Thank you. My name is Terrence Smith, and rather than reading my bio to you, because you're probably not really that interested in who I am, let me tell you why I'm doing this session. So in my capacity as a TAE at GE, I've probably analyzed 200 or 300 events. And then as my capacity in a leadership role in that same team, I've probably been consulted on an equal number of events. And so I have analyzed a lot of events and looked at a lot of events and have been able to bring just about all of them to conclusion and figure them out. And so what I hope today is to share with you some tools and tactics to analyze the events. And with doing that, what I'll talk about is some of the tools that we can use. And also, we'll talk about, when we talk about the tools, the most important tool that we have, which is our own brains. And we'll talk about a sort of process or a set of questions that I have developed that helps me zero in on where the problem is and bring an event or a problem or a mishap to a conclusion, right? And then, and we won't spend a lot of time on that, right? We'll just spend the first few slides on that portion. But the bigger portion that we'll spend most of our time on is we'll look at some actual events, and we'll go through those events and we'll see how some of the tools that I've talked about, especially those questions that we can develop and use our brains to figure stuff out, we'll look at how those pertain to some of those events. And then at the end, if I manage my time well, I should leave a little bit of time so that we can address some of the questions that come in. All right, so let's talk about some of the tools that are available to us. And so one of the best tools that we have is oscillography. And so most protective relays can capture, most microprocessor-based protective relays can capture oscillography. Now, what's that good for? If we look at this diagram here, we can see that this is a reciprocating load. This is actually a reciprocating compressor, the motor that's driving that compressor. The top three waveforms there are the currents. The bottom waveform is the voltage. But, the actual oscillography record should be the raw data that's captured from the relay. And that's what we're seeing here. Now, for me, this is interesting. It can tell me some things, like, for example, because I see that this is a reciprocating load, I know that this is a reciprocating compressor. But oftentimes, the data that you're looking at here isn't particularly helpful. For example, as I look at this data, that top waveform is A-phase current. Bottom waveform is A-phase voltage. Now, if you were really good and a really visual person, you could probably determine that the angular difference or the power factor between that voltage and current, but I'm not that good. So, one of the things that I really mainly use oscillography for is to look at the actual phasor diagrams. And so looking at this phasor diagram, I know from this that, A-phase voltage is sitting at 0 degrees and the current is sitting at minus 32 degrees, and that's a power factor of around 86, 87%. And that's how I usually use oscillography. I use the phasor diagrams from the oscillography. Now, one of the pre-questions that came in, well, it wasn't one, several of the pre-questions that came in were, what's the best oscillography viewer tool to use, or what tool do you use? And between me and my team, we all either use Wavewin or we use the free Comtrade viewer that comes with our setup software. Now, probably I'd say maybe 60 to 70% of the TAEs in grid automation for North America, they probably use WaveWin. What I'm going to show you here and what I still use is the free viewer that comes with UR Setup. My colleagues and friends, they all think I'm old school and they say WaveWin is better, but I've never not been able to use this to bring an event to conclusion. And so I just use the normal version of UR Setup. It's a ComTrade viewer. It will open and view any event record that uses the IEEE format of ComTrade. Just about all of the GE relays use that IEEE format of ComTrade. Another thing that I should address at this time also is there were a lot of pre-questions about the ins and outs and how to use the particular viewer. I didn't really address that in this presentation because I didn't really know what viewer you might be using. There were also some questions around how to set up the relays and the devices for oscillography capture. And so I've taken that feedback, and so we're going to start working on some how-to videos on how to view some of the ins and outs of how to use the ComTrade viewer that comes with UR Setup. And we're going to create some how-to videos around how to set the oscillography to view. Now, when those become available, they'll be on the how-to video section of our resources page. So you can always find those sort of how-to videos as well as this video in the future on our resources page. That page is resources.gegridsolutions.com. GE Grid Solutions all being one word. So there's a few things about the oscillography and the oscillography viewer. Let's look at some of the other tools. Another tool that you have available to you is the event file that's available in the relay. So the event file is basically the time-tagged sequence of events that happened in the relay. So what that will tell me is every flex operand or every operand that's in the relay, it will tell me when it came in and at what time. Well, every operand that has events enabled for it, because sometimes you don't want to fill up the event record with events like sync check okay or sync check op, and so you might not enable events on that. But for most things, you want events enabled. And what this is really good for is it's telling me that a particular operand came in at a particular time. And then I might even be interested in looking at the time differential between those two. So for example, my green trace is where I have pickup of a voltage differential used for a capacitor bank. And the blue highlight on the screen is when that same element dropped out. And then up at the top, the yellow, that 243 milliseconds, represents the time difference between the green and the blue trace. So for event records, they are really good for this thing happened at this time. The oscillography records are a little bit better at telling me what has happened and at figuring out if it should have happened correctly. Outside of the relay, there are also things that we need to do to troubleshoot the physical world. And oftentimes we'll find that our problem exists outside of the relay. And in those instances, we need to use the tools that are available, like this multimeter that I show here, to troubleshoot the physical world. And these are things like, do I have a short in my CT circuit? If I have a short in my CT circuit, my relay is probably not going to operate correctly. If I have a blown fuse, if I have a blown fuse on my VTs, I don't really have an operate signal for my voltages. And for that matter, oftentimes voltage is either a polarizing quantity or a restraining quantity. And if that's the case, then I may not have proper restraining quantities or proper polarizing quantities, and those sort of elements wouldn't work correctly. You know, I might have things like a sneak circuit in my breaker trip circuit, and I want to find those. Those are things that might exist in the physical world. Another common problem is if you've got a 52A, which is a breaker auxiliary, wired to and you're expecting a 52D input or vice versa, your device, your protective relay, for example, is going to think that the breaker status is different from what it is. And for things like motor relaying, that could cause some real problems. So, for example, the relay might think that the motor's running because it's getting a 52A, and it's actually set as a 52B. And that could cause problems when you actually try to start the motor. And so the last troubleshooting tool that we have available to us is our brains, right? And thank goodness for that. You know, if we think about the thing that allows human beings to exist where we do in the food chain, the thing there is that really allows us to exist here is our brains and our ability to solve problems. And so if we think about our brains and how to solve problems, what I've sort of developed over the years is certain troubleshooting questions. So questions I can ask that help me to isolate the problem, identify the problem, and bring it to a resolution. So let's look at those questions. So the first thing is, where is the problem and where is it not? So for example, if I had 5 motors at a site and all 5 of them were the same and all 5 of the protective relays were the same with the same settings, then, my answer to that would be the problem is on this one motor, but it's not on the other 4 motors. And it's on this one relay, but it's not on the other 4 relays. That sort of helps me start to, isolate the problem. One of the things we want to do is get the problem to as small of an area as possible to bring it to resolution. So the next question I would typically ask is, well, what is unique about that motor, right? So if I'm looking at those 5 motors and that one motor that's tripping has recently been rewound, that would be something that's unique. And that would be something that I would want to zero in on as I started to try to solve this problem and figure out what was going on. Another thing is, when did the problem start, right? So using this same example, if I said, okay, this problem started immediately after we had it rewound, that would make me even more suspicious that there is something amiss or something that happened during the rewinding of that motor. And then the next question is something that I often ask is like, how can I isolate the problem to as small an area as possible, right? And so when I first start looking at a problem, the problem could exist anywhere in the world, right? Or the whole world could be my problem. So I want to really start isolating the problem. And so what I like to sort of describe this, since I'm an engineer and a lot of you guys are engineers that work in this field, the way I would sort of describe this is, if you look at a waveform like that oscillography waveform, a lot of times there will be a signal there, but there'll be noise that rides on that signal. So what we want to do is we want to filter out all of that noise so that we could focus on the true signal. And so isolating that problem to as small an area as possible, that's one of the ways that I'm going to filter out a lot of the noise. And so a lot of times when I'm trying to isolate that problem, I'll do things like that help me, or troubleshooting techniques, or I'll ask for troubleshooting techniques to be done that will help me determine, is the problem in the relay or the outside world, right? And once I've isolated it to one of those two places, then that can give us the ability to start working on one of those two places and then narrowing it down further and further. So if we go back to our same example that I mentioned earlier, we've got 5 motors, 5 motors. One of them came back from the rewind and it started tripping. So if I took one of those other relays, like an 869, for example, which has a draw-out case, and I drew it out of its case from the motors that aren't tripping, but put it into the case for this motor that is tripping, and if it exhibits the absolutely same behavior as the original motor relay, the original 869, then that lets me know that this probably isn't a problem inside the relay. It really starts to make me think that it's something around the rewind of that motor. And then one of my favorite things to ask is, am I jumping to a conclusion, or am I merely trying on theories? So if you've ever done if you ever fancy yourself as a small engine mechanic, you've probably tried on some theories. Fuel pumps and carburetors for small engines are fairly inexpensive, and you can try on theories. But in our world, it's not that cheap to try on theories. So we really need to avoid jumping to conclusions because it's going to be costly if we do. And we should really try to avoid just trying on theories or, randomly trying things to see if it fixes the problem. We really need to use this process that I described to sort of zero in on the problem so that we can truly solve the problem. And then the last thing that is the most troublesome is, does my theory explain everything? So at some point, as you're bringing this resolution or this problem to a resolution, you've got to come up with a theory of what the problem is and what the solution is. And if your theory does not explain everything that you're seeing around the problem, then you really haven't solved the problem. You may have made the problem go away, which may or may not be what you're interested in, but if you really want to solve it, you have to have a solution and a theory explaining things that explains everything and every piece of the problem, and not just make the problem go away. So with that said, let's take a look at some of these events, talk about some of these events and see how this sort of technique applies to real world cases and how we can bring some problems to resolution. All right, so let's look at this first event. So this first event is a generator relay failure to trip on loss of excitation. So here's the story. They lost the exciter. Now at this point, the appropriate question is not to ask where they last saw the exciter at, because that's not what they meant. They meant they tripped the exciter offline. So the exciter's been tripped offline, and they have a loss of excitation element, and they expected it to trip, but the loss of excitation element didn't trip. And so let's look at those questions. Well, where is the problem? Where is it not? Well, this is the only generator on this at this site, and this is really the only generator relay at the site. So there's nothing that we can really be unique about where it is and where it's not. Nothing really unique about the situation as we know it so far, the problem as we know it so far. Well, when did the problem start? Well, this is the first time they've had an exciter trip since the facility since the G60 wasn't a G60, I think it was a G30. since the G30 has been installed. So this is the first time they've lost the exciter. G30's been in service for 4 or 5 years. 4 or 5 years, but this is the first time they've had a legitimate loss of the exciter and the relay did not trip. So this problem may have existed the entire time this G30's been in service, or it may have developed recently. We don't know the answer to that. So how can I isolate the problem to as small an area as possible? Well, let's start looking at the actual event. So let's take a look at the oscillography. So as I look at the oscillography record, what I sort of see is the waveforms. Now, what I'm seeing on the currents, so the top three waveforms are I think those are the terminal currents, and the bottom three, I believe, are the neutral side currents, or vice versa. At this point, I don't remember. At this point, it's one or the other. But what we do know is I see a ring down in those currents, and that ring down in current does look like a loss of excitation. Now, those healthy waveforms in the middle of the diagram, those are the voltages. Now, what I see on the bottom is when you set up the oscillography, you can configure the oscillography to record digital states. And so as I look at the digital states in the bottom, what I see is the 40 function, which is the loss of excitation function, is not operating. So I don't see it picking up here. And since I don't see it picking up here, we know that the story as we know it so far is correct. They've had a loss of excitation event, exciter tripped offline, but they did not operate. So let's take a look at what we see. So first of all, let's look at the phasors from the actual waveform that we just saw. So here's the phasors. If we look at VA, so the blue wave, or the blue phasor, is the A phase voltage. The red phasor is the A phase current. So right off the bat, I'm really suspicious around the current being in the opposite direction of the voltage. That's not how a generator really ought to operate. If I take a look at this generator, you know, these are basically machine limits for the generator. And the real power axis along the middle there, and there's a reactive power axis that's to the left there. Now, where we normally expect the generator to operate in is we expect it to deliver some real power. So we would be somewhere along that real power axis. And typically, a generator is run overexcited. And so when we're operating under normal conditions, you know, we would be to the right on the real power axis, and we would be above the origin on the reactive power axis because we'd be a little overexcited. Now, in this case, you know, we expect to be underexcited because we lost the exciter. So I would sort of expect my operating point to be along the real power axis, but down in that underexcited region. And the reason for that is that, you know, when we lose the exciter, we haven't lost the prime mover. So we're still providing some real power to the power system, but we don't have the exciter, so we're drawing bars for the excitation. So it's acting like an induction generator without the exciter. But that's not what I'm seeing at all. Since the voltage and the current are in the opposite direction, instead of being along the real power axis, I'm to the left of the origin. It looks like I am consuming real power from the power system, and I'm underexcited. It's as if the generator it's as if the generator is acting as an induction motor and drawing real power and bars from the power system. And we know it's not acting that way. And so this is problematic for the loss of excitation element, because this particular device, this was a G30, a UR relay, a G30. What it does is it uses an offset distance element to detect loss of field or loss of the exciter. And so basically what it would do is on a resistance reactive diagram, if we're providing real power, we should be somewhere along, we should be somewhere to the right of the origin along the resistive axis. And when we lose the exciter, and we should also be, somewhere to the above the origin on the reactive axis. When we lose the exciter, what we ought to do is our apparent impedance point ought to move down into one of these impedance characteristics that I show on the screen. The apparent impedance point would move, along the x-axis in the reactive way, so it would be below the origin, and it would also move in because we're not able to provide as much real power, as seen by the ring down in current. And so we would move into one of these regions. Now, since the voltage and current are in the opposite direction, instead of moving down like we see there, our actual apparent impedance point would be to the left of the origin, and we would go up and over rather than down and through. And so that's why the loss of excitation element didn't operate. It looks like there is a wiring problem with the currents. And so that brings up the question. If I say something with your current is not right, it looks like the current, your terminal current, is backwards. Then the question then becomes, well, then why don't I trip on differential, right? Because if the terminal current's backwards, I should trip on differential. And it's even a little bit more nuanced than this, because the generation site, basically the way they take the generator offline is they will trip the prime mover, and then they will allow the reverse power element to trip the generator offline. And that has been working correctly the last 5 years that this G30 has been installed. So why aren't we tripping on differential if we have a current wired backwards? And how can we be correctly tripping on reverse power if we have a current wired backwards? Well, this comes into that, that last question of, does my theory explain everything? If my theory doesn't explain everything, I could make the problem go away. I could make it worse in this particular instance. So instead of jumping to conclusions and trying on theories, I need to be able to explain those two elements that seem to be operating correctly. So let's take a look at those. Let's look at the differential. All right. So what I'm seeing on this screen is this is a phasor diagram from the oscillography record that's showing the currents as well as the voltages. And so what I'm seeing there, the blue phasor is the A phase voltage. The red phasor is one of the generator currents, and the purplish color, the sort of the light gray color, is the other generator current. Now, this particular relay is a G30. Now, there's something unique about a G30 in that a G30 can be a unit protection device. So what that means is inside of the generator differential, we can include a transformer, which is exactly what we've done here, which is why you're seeing the 30-degree phase shift on the on the red trace. Normally what we expect to see happen is we expect the currents to be 180 degrees from each other on a generator stator. We don't see that here because it's got a transformer in there. So when we take a look at the actual settings with this, what we see is, so what's wrong with the 40 function? So generator differential looks like it is wired correctly, right? I've got that 30-degree phase shift. Once I account for that, and I account for that transformer differential settings, or the winding settings of the transformer, it takes care of that 30-degree phase shift. So the current differential looks correct. Voltage sort of looks correct. But let's take a look at the actual settings. So when we look at the signal source settings, there is a signal source that is using the M1 currents for the generator diff, and there is a signal source that's using the F1 currents and the F5 voltages for the generator. And the signal source that is sourcing the loss of excitation element is that generator signal source. So using the F1 and the F5 currents, that means we would be using the red currents and the blue voltage to source this element. So it looks like it's in the reverse direction. So and when I looked at the generator directional power element, I see a similar thing. It's using the generator source, but the generator, the directional power element, instead of being set for a reverse power element, it has been set for a forward power element. So what it looks like has happened here is during testing and commissioning, the relay tripped when they picked up load, and it tripped on generator differential. And so they knew that one of the currents was wired backwards, so they swapped one. And they swapped the wrong one, it looks like. And then most likely what happened is when they started picking up load, and then they tripped on the reverse power element, because even though it was set to reverse power, it was being sourced by a signal source that looked like it was in the reverse direction. So they tripped. So it looks like they then changed the reverse power element to a forward power element, which now is in the reverse direction, and they didn't think about the 40 function or the loss of excitation function. So really, it's a difficult fix, but the fix for this, the only legitimate fix for this, is to legitimately rewire the VTs, both sets of VTs, and swap them 180 degrees. This error could have been found earlier during commissioning if they had compared their voltages to their terminal currents of the generator and seen that the terminal currents, which would be the F1 currents, are in the reverse direction from the terminal voltage. And then they would have known that they had wired this incorrectly. So, long story short, there is, you can't just jump to a conclusion or try on theories until you've explained the other pieces of this event, which those other pieces were the reverse power element and the differential element. Okay. So this is another interesting event. A fault on a distribution system causes unusual transformer high side currents. And this particular event, I use this event also to talk about symmetrical components. Now, the symmetrical component talk that I did earlier in the year, if you haven't seen that yet, that's available on the same resources page. On the same resources page that I mentioned earlier. resources.gridsolutions.com. And most likely you've forgotten it. If you did see it at the first of the year, you've probably forgotten about it because it's not that memorable. So we'll go through it again. So here's our story. A distribution transformer feeding medium voltage overhead distribution. So what this distribution transformer is, this is a utility distribution, overhead bare conductor insulation, feeding residential or industrial loads. In their oscillography record, what they notice is that there are two phases of fault current on the high side of the transformer for what they perceive to be a single phase to ground fault on the low side. So, where is this problem? Where is it not? They're actually seeing this at multiple sites. They see this at multiple sites. So there's nothing unique about where it is and where it isn't. They're seeing it on all their transformer relays. When did the problem start? Well, they're seeing this every time they have a single phase to ground fault on their distribution system. And distribution system, medium voltage distribution systems, are subject to things like lightning strikes. It's subject to things like tree strikes. It's subject to things like squirrels who can breach across the insulator and cause a phase to ground fault. And so medium voltage overhead distribution like this has faults, and there's typically a reclose that takes care of that, so it's not that big a deal. But explaining this particular event was sort of puzzling. When did the problem start? They've always seen this problem. So let's take a look at the oscillography record. So here's what we're seeing. We're seeing the top red waveform. That's A phase current on the high side of the transformer. The next current down, which is sort of the orangey type color, is the B phase current on the high side of the transformer. And then we look at the currents below, we see a lot of current on the orange type current, which is the, down below, which is the, again, this is the B phase current on the low side of the transformer. So we're seeing two phases high on the primary, one phase high on the secondary. So let's take a look at the transformer and let's see why we would probably be seeing this. So this is the delta to Y transformer. And so in a delta to Y transformer, the way that the VT connections are made up, or not VT, but the power transformer connections are made up, is that we create our phase-to-phase voltages and ultimately our secondary voltages, which are phase to ground, through a connection of the transformer. And so if we look at this, and we look at the way this transformer is made, what's directly in phase with the B phase current on the secondary, that would be little b on the screen here, we go through that winding, it is exactly in phase with the winding that's right across from it. And that winding is made up of a combination of the B phase voltage or current and the A phase voltage and current. So from the way that the transformer is connected, it creates what we should expect to see for that B to ground fault on the secondary of the transformer. We should expect to see an increase in B phase current and A phase current on the primary of the transformer, which is exactly what we are seeing in this oscillography record. So let's take a look at that. Here are the pre-fault values. Now the reason that I know that this is pre-fault values is because if you look at the oscillography that's sitting in the background there is a green trace that runs up and down the screen. And that green trace, I can move it from right to left in the oscillography record. And since I have the green trace turned on in the in the actual phasor diagram, and I know it's on because my values are in green. I know I'm at the pre-fault values. Now, what's interesting about this is I've set the setup software, the UR setup software, the ComTrade viewer in it, to calculate my zero sequence components. So zero sequence, positive sequence, and negative sequence components. So if we take a look at that, you know, F1, which is the current that are on the primary of the transformer, are, you know, those are my symmetrical components from that. So I've got like 0.12 amps on as positive sequence components. I've got almost 0 amps, a little bit of negative sequence component, 0.04, and I've got almost no zero sequence. I'm going to call that 0. And that's on the transformer primary. Now, when I look at the transformer secondary, what I see there is I see some positive sequence components of 0.5. I see some negative sequence components of 0.14. And I see my zero sequence components being almost identically equal to my negative sequence. Now, this is sort of what I expect for a distribution system like this, because overhead distribution like this has lots of single phase taps, and it might have single phase load. Now, what that means is that it would be next to impossible to completely balance a distribution system like this, because you can never predict when someone's heat pump is going to kick on. You know, if I'm on A phase and my heat pump kicks on, it's going to pull a little bit more power than, you know, when my neighbor may be on that B phase and the other neighbor may be on C phase. But because of the diversity of the loads, it's going to be next to impossible to completely balance a distribution system like that. So because of that, we're going to see on the secondary, the transformer, we're going to see some zero sequence components, like 0.13. And because of that unbalance and because of the way the sequence networks interact, we're going to see some negative sequence components that should be identical to the zero sequence. And that's about what we see. Now, the whole reason we use a transformer like this is because we don't really want to coordinate our transmission line protection, our ground protection on the transmission line, with the ground protection on the distribution system. So we use this delta to Y transformer here to block those zero sequence currents from the transmission system, which is exactly what we see. I0 is essentially 0. Now, that unbalance out on the distribution system, it will manifest itself as some negative sequence current on the transmission system, which is exactly what we see in 0.14. So this is nothing really unique here. This is not really even a problem. It is what we expect to see for a legitimate B-phase fault out on the distribution system and the subsequent currents that we should see on A and B phase of the primary of this distribution transformer. Now, let's look at the fault values. The fault values are also interesting because, so now I've moved my green trace, as you can see, to the fault area. Now, what I expect to see now is I should see on the transformer secondary, I should see all of my sequence components equal. And if I look at the last three quantities, that's exactly what I see. I see my positive, negative, and zero sequence components of the transformer secondary. They're in equal magnitudes. In the next slide, I'll talk about why they are, but it's really because of the way that the sequence components interact. When I look at the transformer high side components, I see something a little different. So again, I don't want to coordinate with the ground protection out on my distribution system. So I'm going to use this transformer to block that zero sequence current, which is exactly what we see with I0 there. It's 0 amps. So now that unbalance or that zero sequence current across the transformer, it'll manifest itself as a negative sequence current. Should be negative sequence current that's equal to the positive sequence current, and that's exactly what we see here. So let's look at why. Why are the sequence quantities of M1 and M2 different? So if we draw the sequence network for the fault, and we look at the current seen from F1, so F1 is going to be the transformer secondary. This is what the sequence networks looks like on the left. Now, since each of the sequence networks, the positive, the negative, the zero sequence networks, since they're all in series, we expect the same current to flow through all three. And that's exactly what we see on the screenshot to the right, where all the currents are essentially the same value. Now, what happens on the primary? Well, the sequence network is a little bit different on the primary. The transformer impedance is not involved because of the way the sequence networks interact. And so because of that, we won't see any zero sequence current. Now we should see positive sequence currents, we should see negative sequence currents. And they should be, since they're in series, they should be of equal magnitude. That is exactly what we see here. So the next question is, well, if this affects the sequence currents, how does it affect the sequence voltages? Or how does this affect fault voltage? Well, normally what we look at and what we see, when we see when we look at the voltages, and we're looking at the transformer's secondary voltages on the top here, and we know that it's a B-phase fault because we can see the currents on the bottom. We can see the B-phase currents are increased. We can see that the B-phase voltages during the time of the fault has sagged. It's sagged somewhat. So, that tells us, and that's what we expect. We expect to see that sag in voltage for the B phase because that's a faulted phase. Now, what that sort of also does for us is we should see some negative sequence voltage, positive sequence voltage, and zero sequence voltage, which is exactly what we see in this waveform. And again, there's more details on how these sequence networks interact and some of the sequence network functions and how to use those sequence networks to look at events. Some of that is available. That's available on the tech talk that I did for that particular subject earlier in the year. It was February or January, somewhere along in there. But you can find that from our resources page. So let's move on to another one. This particular event is incorrect current transformer wiring causes bus fault during a power transformer energization. Now, and we are now getting into some of the events that really make my head hurt because they're a little bit more complicated and a lot of them involve some wiring issues. Let's take a look at this first one. Here's the story. The story is they've energized the transformer. Now, but as soon as they picked up load, they got a transformer differential. Now, a lot of times you might operate on a transformer energization. So there's a way to restrain the transformer differential for the inrush associated with a transformer energization event, and that's called harmonic restraint. And usually it's second harmonic restraint. My colleague Dan Ransom did a great tech talk on that one, on that particular subject, just on transformer inrush and how to restrain for it, and that's on our resources page. But in this particular event, they've energized the transformer. Transformer's been energized for some time, but they don't trip until they pick up load, and they do trip on transformer differential. Well, let's see if we can isolate this problem. So where is the problem and where is it not? Well, as it turns out, there's actually two transformers at this site. And both transformers have been wired, the relays for both transformers have been wired the same. This problem, as soon as they pick up load, they get a transformer differential on this trip. It only exists on one of those two transformers. They have verified the wiring from the CT all the way to the relay. And both transformers and both transformer relays are wired identical. They are drawn identical. They are, on the drawing itself, they are wired identical from the CT all the way to the transformer. So one of these transformers has the problem. One of these transformer relays has the problem. The other transformer relay doesn't have the problem. So what is unique about that transformer that has the problem? Well, at this point, we can't figure it out, right? At this point, I don't have enough information to figure out or know what's unique about this transformer that has the problem. And for that matter, two transformers, they're the same size. Same protective relay on both transformers, same wiring, same nameplate information. So there's nothing that I can do. Something has to be unique because it's something in either the relay or the transformer has to be unique because it's operating. It's tripping as soon as they pick up load on one of the relays, but not the other one. So when did the problem start? Well, this is sort of a new installation, so this problem has started, it's potentially, or every way we can think of this, it has been there since the install. Is there a way that we can isolate the problem to as small of an area as possible? That's going to be something I'm going to focus on my troubleshooting and my event analysis. And also I want to make sure that I'm not jumping to any conclusions or trying on theories. But since we do have oscillography, we ought to be able to at least understand why the relay is operating. So let's take a look at that oscillography. So here's the oscillography again. You can't make a lot out from this, right? So at the top are the one set of currents for the transformer. At the bottom, the red is the A phase, the yellowish orange color is the B phase, and the blue is the C phase. And same for the next set of currents. So I can't make out a lot from this, but I can from the phasor diagrams, right? I do know that I am seeing a percent differential operate. I see that in the digital at the bottom. So let's take a look at the oscillography record. Or we're already looking at the oscillography record. Let's take a look at the waveforms, right? So let's look at the waveforms. Not a lot of interesting things to see here. So let's move the A phase currents, the high side and secondary A phase currents, to one graph, which is on the right, and that's the red phasors. The middle phasors that are the yellowish orange color, that's the B phase, and the blue phasors are the third phasor diagram there. Now, again, this is a transformer, and what I can sort of say is that since the F1 currents are larger, can I say that? Since the F1 currents are larger than the F5 currents, I can probably deduce that the F1 currents, if I'm looking at the primary quantities, which I am, that's probably the secondary of the transformer because it's larger. So that means F1IA. So the primary currents, I've got F5 at 0 degrees. So if I look at my phasor diagram 1 with just the 2 red vectors on it, the one that's sitting at 0 degrees is a phase primary current. Primary current to the transformer, to this power transformer. Now, right off the bat, something doesn't look right to me. Now, what doesn't look right to me is most transformers are 30-degree lagging transformers. And that doesn't look like a 30-degree lagging transformer to me. Let's take a look at it. So let's take a look at what we expect to see. For ABC rotation, as mentioned earlier, you know, A phase is made up with a combination of A and C currents. So if I look at that bottom winding, you know, A phase on the second, or A phase on the secondary, which is the Y winding, is exactly in phase with the A minus C currents, right, because of the way the transformer is made up. So what that looks like is A minus C is my little a, which is my secondary current, ought to be at negative 30 degrees from my primary current. And that's how most transformers are made. And that's not really what I'm seeing there. Now, what I'm seeing there is it's at minus 150. Now, that's okay. That's okay because of the way we actually wire the CTs. I expect it to be that minus 30 minus the minus 180. So what I expect to see it at is at minus 210. It's really sitting at minus 150. Now, if it's sitting at minus 210, the actual current, that means it's a 30-degree lagging transformer. And it's not. It's sitting at minus 150. Now, if I look at the actual winding currents, and these are the settings in the relay. Winding 1 is the reference winding. And the second setting from the bottom there is the angle with respect to winding 1. Now, there's not really a winding on winding 3, so ignore that. Well, there is actually. But if I look at winding 2, that angle is at minus 30 degrees, which would be correct for a minus 30-degree lagging, or a 30-degree lagging transformer. But this current was sitting at minus 150 instead of minus 210. That setting doesn't look correct for the currents that are applied to the relay. For that setting to be correct for the currents applied to the relay, that would have to be minus 330. Because if we think about, you know, what's 180 degrees from minus 330? Well, that's that 150, minus 150 that we actually saw. And so that, for this transformer to not trip on differential, that needs to be set to minus 330. But there's a problem. And the problem is if the other transformer is set to minus 30 and it's not tripping and it's wired the same way, right? So I can't just say that they need to swap that to minus 330. That would make my problem go away. That would make my transformer differential problem go away. This trip on differential every time they picked up load, that'd make that go away. But I can't say that I've solved the problem because I can't explain why the other transformer is wired the same way, has the same settings, but isn't tripping, right? Let's take a look at this. Yeah, typically the H winding leads the X winding by 30 degrees. So it'd be a 30-degree lagging transformer. I also didn't mention that I got nameplate drawings for the two transformers, and they're both 30-degree lagging transformers. So they're both the same transformer. I can't at this point explain why one of them's tripping and why one of them's not. I know that setting that to minus 330 takes the trip away, but I haven't solved the problem because I can't explain why one of them's tripping and why one of them's not. So let's take a look. Well, again, what I expect to see, this is what I expect to see for a minus 30-degree lagging transformer. I expect the currents to be at minus 210, right? So if we zero in just on the red vectors there, that's primary current at 0 degrees, secondary current at minus 210. That's what I expect to see, because if we flop that vector around 180 degrees, it's sitting right there at minus 30 degrees. Now it's sitting at minus 210 versus minus 30, because if we look at the left, the way that we wire the CTs is we're wiring polarity to the side of the CT that is away from the protective equipment, which is typically marked as polarity on the CT. And since we're doing that, what that means is the current flowing into polarity on one side of the transformer, the one side of the current, one side of the relay inputs, it's wiring flowing out of polarity on the other side. So we expect to see that 180 degree phase shift. So instead of being at minus 30, we expect it to be at minus 210, which is what we're seeing in this screen. Now, what we were seeing on the previous slide, though, was we weren't sitting at minus 210, we were sitting at minus 150. But it's even more nuanced than that. What we're actually seeing here isn't ABC rotation. Let's take a look at what we're actually seeing. All right. So if we look at these phasor diagrams, if our eye was at the right side of the screen and it was looking into the origin, as these phasor diagrams rotated counterclockwise, what we would expect to see is we would expect for ABC rotation, we would expect the A phase current to pass our eye, and then the B phase current, and then the C phase. Now, as we look at these, that's not happening. In fact, the phase sequence is red, blue, yellow. And red, blue, yellow corresponds to an ACB rotation rather than the normal ABC that we're expecting. So this is starting to clue me in on what could be wrong here, right? And so one of the things that I know from some previous events is if we take a transformer, right, and instead of applying ABC to it, instead of applying H1, instead of applying the A phase to H1, and instead of applying, C phase to H3, if we swap those two, we're going to have a different transformer. Instead of IA being at minus 30 degrees like we normally expect, we'll see what we see here, and IA would be at positive 30 degrees. It would be leading by 30 degrees if we merely swapped the A and the C phase. Because if we took the A phase and connected it to H3 on the transformer, and we connected C phase to H1, and then we did the same thing on the X winding, the secondary bushings. If we connected A phase to X3, and we connected C phase to X1, we'd sort of take care of any issues, but now we would have a 30-degree leading transformer. We'd also have ACB rotation. So, how do we fix this, right? So, ultimately, the trip occurred because of settings, right? That setting of minus 330 is wrong, or minus 30 would be wrong. For this particular transformer, it needs to be minus 330. But it's more nuanced than that. And the reason I say it's more nuanced than that is because the actual problem here, the reason that the other transformer wasn't tripping and this was tripping is because the two transformers faced each other. And there was a piece of strain, or there was some strain bus that ran between the two. And so if we assume that the strain bus ran from north to south, That means as we look west, we would see one transformer. As we looked to the east, we would see a different transformer. And the problem is if we look to the east, we would see, if we look to the east and we look to the bushing to the far left, that would be H1. But because these transformers were facing each other, they would be mirror images of each other. And so if we look to the west and we look to the transformer to the right, or the bushing to the right, that wouldn't be H1. That'd be H3. And so what ended up happening here was the strain bus was connected, A phase was connected straight across to the first bushing, B phase, same thing, C phase, same thing. But because of that, the transformers were wired identical. On the secondary to CTs, the relays were wired identical, but because we had wired C phase to H3 on one, and we had wired, C phase to H1 on one of the transformers, and A phase to H3 on the other transformer, because of that, we had this phase shift, and that was problematic. So is this a problem? Well, it is a problem if we intend to parallel those transformers, if there's the possibility of paralleling those two transformers anywhere in the power system. If there is, that means that what we're calling A phase is really at a 30-degree angle, or actually it's a 60-degree angle to B phase. That looks more like, phase to ground voltage appearing across what we think is A phase. That's a problem, a big problem. If we ever parallel those, there's going to be enough circulating current that it's going to damage equipment and probably damage these transformers. So if that's a problem, then we need to change the primary connections. That was the problem that was a potential in this particular case, so they had to change the primary connections to the transformer. So again, we could have solved the problem. We could have made it go away by merely changing that to minus 330. We would not have had those trips anymore. But if we ever paralleled but since we just made the problem go away, and we didn't actually solve the problem, if we ever paralleled those two transformers in the facility, we were going to potentially destroy one of the transformers. So you've got to explain everything, including why one of the transformers is tripping, one of the transformer relays is tripping, and the other transformer relay is not. All right. So this is an operation of a motor relay. So a reversed phase causes motor thermal overload trip. So here's the story. The story is they have a brand new switchgear. Switchgear is feeding motors. So these are medium voltage motors. They're pretty big motors, and they don't switch them very often. So they're feeding them with switchgear rather than a motor control center. Not unheard of. When they start the motor, it trips after about 10 minutes. Now, it's a whole switchgear lineup with multiple motors being fed by the switchgear lineup. And this is the only switchgear in the lineup that is feeding a motor that trips when they start the motor, or after the motor's been running for 10 minutes or so. None of the rest of them are having this problem. So where's the problem? Where is it not? On this one switchgear, this one motor, but it's not on the rest of the lineup. What's unique about it? I don't know at this point. I've got to sort of look at the oscillography record and figure that out. When did the problem start? This is a brand new switchgear. So since it's a brand new switchgear, it's probably always been there. Let's take a look at it. So here are the waveforms. Now, what is really unique about this particular one is that if we look at these waveforms, if we look at these waveforms, one of the things that we'll notice right off the bat is I can't really tell what's happening by just looking at the waveforms. I can't tell what the phase sequence is. I can't tell very much of anything. But what I can tell is if I look at the phasors, immediately, right off the bat, what I can tell is that one of these phasors is not, or one of these currents is not correct, right? So the phasors that you see there, the vectors that you see there, those are the vector diagrams for the currents to the motor. And looking at this, it looks like the red vector is in the wrong direction, right? So take a look at that. The red vector is in the wrong direction, so it looks like if I merely swap polarity and non-polarity on the red current, that I can take care of this problem. Now, there's a couple of questions here. The first question is, well, why is it taking 10 minutes to trip? The other question is, that can completely solve the problem. So let's take a look at it. Clearly, there's a phase reversed. Why is it taking 10 minutes to trip? Well, as we know, you go to several tech talks and see lots of tech talks about me or others explaining the motor thermal capacity. But basically, what the relay does is it models the thermal capacity of the motor. And so basically, the best way to think of this model is this red lava-like fluid that's filling up the beaker. When the beaker becomes full, we trip. We trip because we have no more capacity for thermal capacity. Now, in the case of negative sequence current or a reversal like this, one of the things that we do is we bias that motor thermal model with that negative sequence current. So this takes care of things like blown fuses, loose connection, things like that. So it is biasing and not tripping. So it takes a little time for that motor thermal capacity to build up that causes that unbalance to trip. And in this case, it took it about 10 minutes. The other problem we should always ask when we find an error like that is that the only error here? Let's take a look. If I take a look at this, the red vectors on the right are the current and the voltage. And right off the bat, I've probably got a problem because I should never have that much of an angle between the voltage and the current. It's even worse. It's even worse because what I'm actually looking at is the A to B voltage, and I really want to compare A to G voltage. So I can do this a few different ways. I can draw a line from B to G to A to G, and that's going to be the VBG or VA vector, and then I can take that vector and just superimpose it on the origin with the V with the the B phase at the origin, or I can take negative VBG. Either way, what it's telling me is that the A to B voltage is going to lead the A to ground voltage by 30 degrees, which in this case, that makes my situation that I just saw even worse because the A to ground voltage is going to be 30 degrees more. So it's going to be more like I've got, instead of almost 90, it's closer to 120 degrees between my actual VAG and my A phase current. So how do we fix this, right? And this is a monstrosity here. In reality, if I look at this, what is really A phase is wired to B phase and it's rolled by 180 degrees. Now I know that because if I take the B phase vector, which is that yellowish vector, and I roll it by 180 degrees, it's going to be sitting down there about where the power factor should be from that A to ground voltage, which would be sitting at minus 30 degrees. So I know what's really what is wired to B phase is really A phase, and it's rolled 180 degrees. So I know I need to fix that, but I don't know what I got to fix on the other two phases. Well, I do know that once I've made that fix, I need to maintain ABC rotation. And so to maintain ABC rotation, then what I can do is I can move the wire from B to A and roll 180 degrees, move the wire from C to B and roll 180 degrees, and move the wire from A to C and don't roll it. So not a single one of these currents was wired correctly to the relay. The motor ran correctly, so it's wired correctly there, but none of them were wired correctly. So merely, had I merely just, inverted and rolled the wires on A phase, the next problem I would have had would be, the metering on the power would look really weird. The power factor that I would be able to meter would look really wrong. But, that might have made the problem go away, but it, didn't solve it and truly fix it. Okay. A few lessons learned I should mention here. Relay had a roll phase, but it also had other issues. And one of the things that you should always do is during startup, you should verify your metered values. Not only should you verify your metered value, but you should verify that your phasors look correctly and that your sequence voltage and currents look correctly. And they should be relative for a motor like this, they should be almost zero. And they should really be small compared to the positive sequence quantities. Other thing is to know we've wired it correctly, we should expect power factor for an induction motor like this to be lagging at 80 to 90%. And that's not what we would have seen on this particular motor. Okay. So the next event is a low impedance bus differential trip when the second breaker is closed on the bus. So the story here is we're installing a bus differential. So this particular relay was a B90 relay. As soon as they picked up load on the bus, so they energized the bus, closed one breaker, no problem. Closed the first breaker on the bus, picked up load, they tripped. Now, where is this problem? Where is it not? There's only one B90 on this bus, so there's nothing really unique here. When did the problem start? This is a new install, so it probably started with the install. So let's see if we can take a look at this and isolate the problem and solve it. So again, here's the oscillography from the trip. We're showing F1, F2, L1, L2, and S1, S2 currents. Now, this is a B90. A B90 can be a phase segregated relay. And so what that means is you could use a B90 in a system where a B90 protects the A phase bus, a B90 protects the B phase bus, and a B90 protects the C phase bus. In this instance, there's one B90 protecting, all three buses, all three phases of the bus. But the way this has been configured is what I'm going to assume is the A phase current had been wired to the F module on the B90 relay. The C phases had been wired to the L module, and the B phases have been wired to the L, and the C phases have been wired to the S, and that's what we see here in the settings. If you want more details about how you can configure a B90 like this, or what the B90 is, again, a great resource is our resources page, resources.gegridsolutions.com. So this is how this is configured. So we ought to see A phase currents on the F, G on the L, and C on the S. So let's take a look at what we see. Okay, this is a monstrosity. This is the sort of thing that makes your head hurt and wonder why you got into analyzing events in the first place. Because if we put the two A phasers on the same graph as blue, the B's is red and the purples as S, purples being C's, the only thing that looks right is the purples, the C phase. Looks like they've got a problem on A and B. So, corrective action here, you got to maintain ABC rotation, right? So that means the blue that's sitting at 0 degrees looks sort of correct, right? So that means we're going to have to take the red phaser that's sitting at 180 degrees, and it needs to be moved from the L module to the F. Or, since this is a B90 and we can configure this, we could change this in settings, and we could correct this in settings. It's always going to look weird if that's the case, but we could do this in settings on this B90. It's rare that we can make this sort of wiring correction on a relay, but in this case we can do this on the B90. So we need to we need to reassign the current, whether moving the current physically or changing the setting from on the L1. And we also need to do the same thing on the F2 and move that to the B phase bus differential, or bus differential zone 2. Okay. And the very last one I've got before we got some time for some questions is a paralleling switchgear trip. So in this paralleling switchgear trip, the story is the relay trips every time I close the breaker. Okay. It is tripping on overcurrent. Right? So what is the problem here? Well, turns out this is a new site. This is a new site. It's a cogeneration site. So there's a generator there. That's their main thing. They're supplying auxiliaries. This particular relay, I think, was a 750 relay, which is about to be obsoleted at the time. This was still going strong. The rest of the 750s are not tripping at the site. It's only this particular one tripping on overcurrent. So that's the only thing that seems suspicious, and it looks like it's been there since the plant was installed, since it's a new plant, and it's only happening when they close the breaker, right? So when we take a look at this trip, phase ABC, right? This is the event record from the 750 relay. We see that it was an ABC trip, all three phases, and it was on a phase time overcurrent. Now, one of the cool things about the 750 is 850 does this as well, but when it captures the event record, it also captures the magnitudes and angles of the currents and voltages at the time of the event. That's what you see in the bottom down here. And what we're actually seeing in the bottom, the A phase current is about 2,400 amps. B phase is 2,500, and C phase is about 2,500 amps. 2,500 amps was what the current that was being measured. Now, the problem here is this is a 2,000 amp breaker, right? So if it's a 2,000 amp breaker and you're going to adequately protect it, that means your pickup on the overcurrent needs to be set at 2,000 amps or less. And so it looks like it should have tripped with 2,500 amps of current. Let's take a look at the phasers. Since we have them, we can. Let's take a look and see what they look like. Same thing. Phasers look healthy. I don't see any real distortion in the waveforms. The A, B, and C phase currents are at the top. So I don't really see any distortion in the waveforms. This looks like a legitimate trip. And I would want to trip if it's 2,500 amps. So the next question that I had to ask was, well, where is this breaker at? What is this breaker doing? And this breaker is a tie breaker in a main tie main arrangement like this. So I'm showing that 750 sitting there on the tie breaker. So the two mains are on either side of it, and they're feeding from the top, and then there's multiple breakers that are feeding the switchgear. The switchgear is feeding the plant auxiliaries, so pumps and things like that. So the next obvious question is, when that breaker closes, what are you paralleling? And the answer I got back initially was, well, we're paralleling the same power system. So I started asking some more questions to see what the same power system looked like or was. And here's what we found, is that switchgear existed here. And there was a 13 kV distribution system that was, fed by the same utility at 13 kV that the cogen facility was connecting to at 230 kV. So what was happening is when that other tie breaker, that other main breaker, and the tie to the 13 kV distribution system, that existed so that they could black start the plant. It was never really meant for those two systems to be tied together. The reason that it was never meant to be tied together is because when you tie those two systems together, instead of feeding that 13 kV distribution system from the distribution transformer and from its normal feed, we are now feeding most of that 13 kV distribution system through that tie breaker and through those two mains. And that's not something we would ever want to do. Now, the reason we're feeding most of that, if we draw the equivalent circuit of that, what we find, this would be the equivalent circuit. The distribution loads on the far right are the loads we would actually be feeding. And the breaker that I show to the right is the actual tie breaker that we would have closed. So what would end up happening is the source impedance of this GSU transformer, the GSU transformer impedance would be much less than the distribution transformer impedance and the distribution system impedance, which are shown on the left hand of the screen. Since those are so much less, then the interconnected grid in the United States would connect through, most of the current would flow through the GSU transformer impedance through that tie breaker to those distribution loads. So there are a couple of options to sort of solve this problem, and none of them are really super. So possible solutions are, you can't parallel these two. They're not meant to parallel. I can't raise the time over current pickup setting on their tie breaker 750, right? We can't really do that because, first of all, those two systems are not meant to be paralleled. Second of all, that's a 2,000 amp breaker. You can't really pick up that, raise that pickup setting above that because then you would not be adequately protecting that breaker. They could add controls to trip a selected breaker after all three are closed. So what that would look like is if they put the 52A and B contacts in series, and so that if all three breakers became closed, they would trip the distribution system main breaker. What they actually did was they added mechanical interlocks to prevent paralleling of the three sources. So they added some mechanical interlocks to the switchgear so that you could never parallel those three sources. Now, so in conclusion, I think I'm going to leave some time for questions. In conclusion, I'll say that one of the things that helps you solve any problem, including any problem associated with an event or event analysis, is that if you have a systematic approach, it can help you separate the signal from the noise and focus on the real problem you want to solve, right? And that is the first step in solving any problem, is maintaining your systematic tool or your systematic problem-solving techniques, staying on those tools, and solving it in an orderly fashion. The other thing I would say is that you really need to know how to use the tools that you have, and that's the next most important step. The first step that I mentioned there, that's using the tool of your brain. And so you really got to know how to use that tool, but you need to know how to use all the tools that you have at your disposal. Okay, first question is to confirm, putting the settings to minus 330 degrees is the same as using, I'm not sure sorry, but I'm not sure that I'm understanding that. I understand why minus 30 angles is incorrect. It just seems using minus 330 or whatever is ambiguous. I'm not 100% sure what this question is around, but I think the source of confusion here is that in the T60, the T30, and the G30, which that relay was, I believe, a T60, the angle has to be set to a negative quantity. So it has to be set to either, you can't set it to 30-degree leading. It has to be set to minus 330, which is a lagging quantity. It has to be set in a lagging quantity. So, that's one of the nuanced things about that may seem odd. And that may be, what is the source of confusion there. But most transformers, if they're wired correctly, and winding 1 is set as the H winding, the high voltage winding, the H winding is set as winding 1. Most transformers are configured with a minus 30-degree setting. Angle with respect to is minus 30 degrees. If there are, a normal transformer that's like 99% of the delta to Y transformers that exist out there. What is the best way to configure the setup or the relay for event analysis? So that is a longer discussion. We didn't really address that today. As I said, we're planning on doing some how-to videos. Those are shorter videos than this. They're only available on the resources page, and those are typically targeted at less than 10 minutes, and it's like how to do a particular thing. So we owe you some how-to videos on how to configure oscillography for a UR relay, and we'll get those published. Okay, there's a lot of questions that are coming in about what is my favorite tool or what tool do I need to use. Again, the tool that I was using to analyze nearly each and every one of these events was the free ComTrade viewer, the ComTrade viewer that comes as a free part of UR Setup. Each of our setup softwares, the UR Setup, the 8S software, the SR3, but the 8S and the UR both have a ComTrade viewer that gets installed when you install the setup software. So there's no license needed for that or product key or anything like that. For the WaveWin, if you get that, there is a product key that is needed for WaveWin. But for me, like I said, I'm old school. I've never not been able to do something that I wanted to do with UR Setup. Probably my Teams chat box is filling up right now from my colleagues who are making the case, that I should be using WaveWin, but I just use UR Setup because I've never not been able to do something that I wanted to do for that. That's what I know. How do I diagnose a ground fault from voltage and current values? So that's a good question. And the second event that I showed should help you diagnose that, right? So, for example, if we see one of the phase currents go high and the other two, they don't go high, that looks like, hey, you've got a ground source. You've got a ground source in your system, and you have a ground fault. Since you have a ground source and a ground fault, the other thing that you should expect to see is not only should you expect that single-phase current to go high, you should expect the same voltage that's on the same phase for it to drop in magnitude. Now, if this is an ungrounded system, if it happens to be an undergrounded system and you don't have a ground source in your system and you have a ground fault, it is a much more complicated thing. If that's the real question you're asking, then you really need not necessarily ground protection, but you need a ground detection system. And for that ungrounded phase, you don't really have a fault when you ground the first phase. But you do need to detect it for subsequent faults. So for that ungrounded system, probably the best way to do that is with a particular VT connection that is a broken delta VT protection. I did not say open delta. I said a broken delta VT connection. That broken delta VT connection is a very particular VT connection that allows you to measure the zero sequence voltage in the system. And with a ungrounded system and a broken delta VT connection, you can identify that you have a grounded phase. Here's a great question. What is the basic data we should ask the customer when the fault reported, and from which data should we start investigating? So what data do you need to investigate? Well, one of the best pieces of data that you can get from the field to start an investigation is a service report. So on all of the GE devices, when you're connected to a relay, you can get a service report from the device. Now, where that service report is when you're connected to the relays, right above the online window, are these little icons. And the icon to the far left, if you hover over that icon, it will say service report. You can click on that, and the relay that you're connected to, it will grab a service report from the relay. And what that service report will be is it will be a zipped up file that will include the settings file, the event file, and all of the oscillography files that are available in the relay. And you can, unzip that file or send it to GE for analysis, and you'd have most of the information that you need. So, at a minimum, the information that you need to really analyze an event are those oscillography files, the event files, and the settings file. Now, in the ComTrade format, there are a couple of ways that there's a couple of different formats you can use. You can choose a single, it's a matter of preferences when you download the files from the relay. If you're just downloading files from the relay, it's a matter of preference in your UR setup if you're doing it with the UR. And you can choose a single file, or you can choose the multiple file format. If you choose a single file, it'll be a CFF. If you choose a multiple file format, you'll get 3 files. You'll get a HDR, a file that carries the extension HDR, a file that carries the extension DAT, and a file that carries the extension CFG. And all 3 of those files would need to be in the same folder when you opened the CFG to view the oscillography, but you need the oscillography. You'd probably want the event record as well, and that would carry the extension .ebt. Settings file is going to be important also. And so the extension that settings file carries will depend on what relay you got. For a UR, that's a .urs file. For an 8S, that's a that carries a different extension. But you need the settings file because typically you're not going to be able to completely solve the problem without that settings file. And then once your investigation goes from there, you may need all kinds of information. Like, for example, we were not able to solve the strain bus, the transformer issue there. We were not able to solve that until we actually had, physical drawings of the transformer and the bus arrangement. I mean, it was very obvious. I mean, we had real deep suspicions that that's what it was, but we couldn't definitively say until we saw those drawings. So we might want the drawings. Another piece of information that's always good to get from the field is what happened, right? What they think happened, or what happened. Just to send the oscillography record and the settings file doesn't really help you start your investigation. But at a minimum, those are the things you need to get from the field. For voltage loads, what type of relay do you recommend to identify transient sag swells for power quality events in general? That's a great question. You know, if I'm just wanting to identify those transient sags and swells or power quality events, if I'm just wanting to identify that, I don't know that I would want a relay. If I just want to identify it, I'm probably going to use a panel mount meter. So what I would probably recommend in that instance, if I really wanted the top of the line, I would probably use something like the EPM 9900, which is the top of the line power quality device that you can get oscillography from. You can identify those sags and swells. You can grab those transient. It has a really high sample rate, so you can get a lot of the C harmonic content all the way up to very high values. If I don't want to have the higher value, there's other power quality meters that we have, like the PQM or PQM2, right? That's a power quality meter that we have. That's another option. It doesn't have the same capabilities as the EPM 9900, but it's another option. For a substation option, we also have the DR60, which is a digital fault recorder.
So the question was, how do I test inrush current with secondary injection? Most modern test sets, you can add second harmonic content to the values that you're injecting into the device for testing purposes. And so you can add second harmonic that is above your pickup or above your second harmonic restraint level, and your device should restrain in those instances, or restrain in those instances. Lots of questions about wave wind versus UR setup, and which is better. Like I said, I'll tell you what I use. Are there different oscillographies that look at raw, unfiltered AC quantities? If so, when should you use them? If you're viewing the ComTrade records, if you're viewing the actual ComTrade records, and you're viewing it on a UR setup or from a UR relay or an 8S relay, what you're going to be seeing in those oscillography records is the raw, unfiltered AC quantities. It's what's connected to the back of the device. So you're looking at unfiltered quantities. When you set up the device to capture oscillography, you can set it up to capture some of what I would call the calculated quantities, what you're probably calling the filtered quantities. So these are quantities like the RMS magnitudes, RMS angles, those sort of things. Those are traces, and you can set the device up to capture those quantities, and then you can view those quantities in the ComTrade viewer of what the F1s and the F2s, all that stuff that I was mentioning is what's wired to the back of the relay. So it is not filtered. It's not filtered on a UR, or when you're looking at the actual currents wired to the back of the relay, F1, M1, all of those. UR or even an 8S, those are unfiltered values. If you capture the RMS quantities as a matter of setting, so you set the device up to capture those RMS quantities, you will see that as a trace below your wired quantities. And then, so those would include any filtering. So those would be like RMS or phasers. One of the things that I always like to include in that is differential current, right? So if I have a L90 or a T60, I can configure the AC inputs to capture my calculated quantity of differential or restraint. You put that into the waveform and see those. Explain the importance of differential function of current analysis of instantaneous and RMS average. And RMS versus average. So the importance of the differential function, obviously, differential doesn't have to be time coordinated with anything, because differential protection has a defined zone of protection, so it's going to operate faster. Now, when it comes to the context of viewing oscillography, the differential magnitude, the differential restraint are always good quantities to put into the settings, the analog settings that you're going to capture in the oscillography record. The reason for that is because then when you view the oscillography, you can view what the relay is actually calculating for both differential and restraint, which is going to help make your analysis much easier. The second part of this question is around what's the difference between like RMS or the phasor quantities. So RMS obviously stands for root mean square. Now, we often take that to mean, well, that's the peak of the voltage or current, peak of whatever waveform, divided by the square root of 2. That's one way to find it. That's the way to find the RMS value for a perfectly symmetrical waveform. But the RMS quantities are actually related to the area, the integration of the waveform, the area under the waveform. So since it's related to that area, it is going to include any harmonic content. So an RMS quantity would also include the harmonic content. Phasor quantities, on the other hand, the way the phasor quantities are calculated is as a Fourier transform of the fundamental quantity. So for the relay is going to track frequency. So here in the United States, that frequency is going to be close to 60 hertz, and it's going to give you the 60 hertz, or the tracked frequency component of the waveform. Now, there is a mechanism in a lot of the overcurrent settings to either set the operate quantity, or UR relays, I know some AS relays, to set the operate quantity as either phasor or RMS. In most instances, you're interested in overcurrent protection of fault. The fault current will be the 60 hertz component. So in most instances, you would want to set that overcurrent to operate from the phasor quantity. The reason the RMS quantity exists there is if you wanted to use the overcurrent to sort of model a thermal element, you would be more interested in the RMS quantities, because the RMS quantities would include any harmonic content, and they would be more directly related to the amount of heat that the device would generate. So if you're wanting to model, some sort of thermal overload for a transformer or something like that with an overcurrent element, then you would want to use the RMS rather than the phasor. If you want to protect strictly for fault current, you'd use the phasor. Another great question here. What is meant by 52A? And you have my apologies for not being more explicit. A 52A is an auxiliary contact associated with a breaker. So since it's an auxiliary contact, it's used for signaling further to relay. So a 52A would mimic the state of the breaker. So in other words, a 52A auxiliary contact would be closed when the breaker's closed. A 52B is the reverse of the breaker. So a 52B contact, it's again an auxiliary contact, but it would be closed when the breaker is open. So in my first example, I talked about how that could be problematic. So if you were expecting a 52A and you'd set the relay for a 52A for a switchgear or a contactor, you'd set it for a 52A, and what you actually had was a 52B wired, then your relay could interpret the closed signal there to mean that the breaker or contactor was closed and the motor was running, when in fact it wasn't. Then when you started the motor, its previous state was running, and that can be problematic because then you could trip on other elements. That's what a 52A is. And you have, again, my apologies for not explaining that earlier. Okay. On the loss of excitation problem, how did you determine a motoring condition when you saw a current waveform near 180 degrees from the voltage? So, to be clear, it wasn't really a motoring condition. It was a wiring error. The wiring error made the generator look like it was operating as a motor. Now, the reason that it looked like it was operating as a motor is because the currents, relative to the voltage, looks like the flow of current was in the real domain was into the generator. So the metering convention is that reverse current. And in this case, since the current's coming from what we thought was the generator terminals, it looked like the current is flowing into the generator. The metering convention for current flowing out of the generator, that would look like current in the same direction as the voltage, or on our phasor diagram, it would be to the right. Yeah, another comment here is that you might even supply that distribution system through your bus. Yeah, that you would not only would you be overloading the breaker, but you're correct in that very last example, you would probably be overloading the bus as well. That's another reason I didn't think of to not do that. Can the oscillography from a distance relay depict a power swing condition? That's a great question, and it depends on a lot of things, right? One of the things it depends on is how long the power swing takes and how long your oscillography record is, right? So a power swing is a legitimate power swing in the power system, not a pole slipping at a generator, but a real, even a pole slipping at a generator. Those are events that they don't take cycles, right? They happen over a much longer time frame than what we're typically used to seeing or thinking about in a protection and control system. And if your oscillography record is long enough, then yes, you could do that. I mean, you capture that. I know in the later versions of the UR relay, if you configure for few records, you can get oscillography records that are close to 20 seconds long, which is plenty long enough to capture the full power swing condition. Also a pain to download 20 seconds of oscillography data from a relay, but nonetheless, you could do that in those later versions of the UR. And again, what that would sort of look like is you'd sort of have to, you'd probably have to calculate the apparent impedance, at different points, and you could see that power swing happen. Here's a great comment. Each of the situations presented could have been solved at the time of testing prior to putting the equipment in service. I agree. Yeah. And the comment's a great comment in that it brings up a really good point, is that testing the devices is very important. But most of these instances, it's not even really a case of testing in the traditional way that I think of testing, where you got a test set and you're injecting quantities. It's more of a commissioning service type testing. So, if they had looked, if the tester had looked at the the quantities that were available as metering quantities on the relays, then he could have discovered that he had errors and resolved them before it caused a trip or before it was put into service. So, Colleen, I think I am at the end of my allotted time. I will turn the floor back over to you to give us your concluding remarks.
Thank you, Terry. Thank you, everyone, so much for attending. Please take a moment to fill out the survey at the end and let us know what you thought of today's presentation. We look forward to seeing you again at our next Tech Talk. This concludes today's webinar. Have a wonderful day.